Okay, so our next speaker, realizing I met over 30 years ago in South Africa. A lot has happened there. He will now be the fourth speaker who has spoken at the mini conference 4 times. I was first speaking here in 1993, so it's been a while. Yes. Okay, and Johannes Hattingh will talk about recent results on the total domination number of maximal outerplanar graphs.
Okay, well, thank you very much to the conference organizers for inviting me. I apologize to Steve, you've heard part of it, but in Chattanooga 2 years ago, but I'm trying to also put it in a different context this time. Of course, the reason 2 years ago, I was also quite aware of the Journal of Computational Geometry. So some of the results actually, not my results, but the results actually appeared there, but using a different notation and different words. And the reason for that is they were looking at art gallery problems, right? So instead of dominate, you want to view and you want to observe and make sure that people don't steal priceless art, for example, in an art gallery. So, for example, if this is an art gallery, I can stand right in the middle of the room, and then I can observe the whole room and make sure that nobody commits a crime in this room, because it's pretty, it's, I guess, a rectangle or even a square. And then, of course, you can eventually transfer the problem's description to graphs and talk about domination. And if you don't want to have dishonest guards, you would introduce total domination. So just consider a simple closed polygon with n sides together with its interior. So here you'll have a polygon consisting of 4 vertices. And then we say a point X in P is visible from a point W, provided that that segment WX does not intersect the exterior of this polygon. So a set S of points is a guard set for P, provided that every point X in P, there exists a point W in S such that X is visible from P. And then the last definition then, GP, is denoting the minimum cardinality of a guard set of P. So GP is just the minimum amount of guards needed to prevent theft from this gallery. And this problem was first posed in 1973 by the mathematician Victor Glee. So is that definition pretty clear, right? Those sort of obvious definitions. And of course, art galleries, sometimes they come in interesting shapes. It's really the case that an art gallery would be just consisting of a square room. Here's the Guggenheim Museum, Bilbao, in Spain. And you see it's quite a fascinating building with all those shapes. So you can imagine how the rooms inside may be looking like. I've read recently that, for example, the Opera House, I think, in Los Angeles also has an interesting shape. In such a sense that when the sun actually shines on the building, it turns into a death ray and actually starts burning vehicles on the road. Right? So they had to obviously do something about the shape to reduce that death ray. So that sort of looks like a death ray building right there. But in any case, the first theorem about this was Châtel in 1975. He said that if you have a simple closed polygon with n side, then you need at most the floor of n over 3 guards to actually guard that polygon. Now you may think, well, I'll come back to that later. If you start thinking about a polygon, you can start triangulating it, and then it forms a maximal outerplanar graph. And of course, it has a Hamiltonian cycle. And then you think, well, any cycle needs roughly n over 3, so what's so difficult about this proof? well, it comes into the floor of n over 3, right? So in a cycle, you may actually need the ceiling of n over 3 vertices to totally dominate. It was a very difficult proof, and then a high school teacher, Fisk, in 1978, actually gave a very simple argument using a three-coloring argument. And Fisk's proof is so short and elegant, it was chosen for inclusion in the proof from the book. So Paul Erdos said that God is a sadist, and I'm not being blasphemous here. He had this wonderful book, and sometimes he opens the book, and then you have this theorem's proof, and you're all happy, right? So this is a proof from the book, and the proof from the book is a book of mathematical proofs by those authors, and it's dedicated to Paul Erdos, who often referred to the book, as I said, where God keeps the most elegant proof of each mathematical theorem. So let's look at Fisk's proof. What you have is that it's called a hair comb, right? And it looks like a hair comb, so it's a polygon. And you obviously want to try to put guards there so that you know, the whole art gallery is observed. And what we are going to do is we're going to try to put guards on the vertices, right? So usually you see people when you walk through an art gallery, they sit next to a wall or in the corner. So that sort of makes sense that you put that restriction on there. The next thing is you start, so this is certainly not a maximal outerplanar graph by any means, and then you start triangulating the interior of that polygon, and so that's the next step. Now, do you all agree with me if I have a guard in every single triangle, right, then obviously you're going to have the whole gallery observed. Okay, so that's the next thing. We have to prove that that's indeed the case, always possible. And it's always possible to three-color a maximal outerplanar graph. And this is now a maximal outerplanar graph using only three colors. And so that's the next step. If you look at the top graph, then we start, for example, with this vertex here, colored red, and then blue, and then green, and then you move on to the next one. That would be red again, because you can't use green and blue again because this is a proper coloring, and so you go on. So in general, you can always three-color any maximal outerplanar graph. And of course, then what happens at least one of those color sets will have cardinality at most the floor of n over 3, right? And so you translate that back to the art gallery, and that then shows that you need at most the floor of n over 3 guards to guard any art gallery. So that was a very elegant and very simple proof. It appears in Journal of Combinatorial Theory as a one-page proof. And of course, you all know Journal of Combinatorial Theory is very snobbish. Yes. So just to recap, the polygon is triangulated. We know it can be three-colored, and then every triangle has three colors. And then the vertices with one color form a valid guard set. And then, of course, we will have at least one of those sets having at most the floor of n over 3 guards. Okay, so next, we could have some dishonest guards, right? They may be stealing some of the artwork in the gallery, right? So we want to make sure that the guards are actually guarding the guards as well. So a guard set S is a guarded guard set of that polygon, provided that every point X and P there is a point W and S minus X, that's where the guarding of the guards come from, such that X is visible from W. And then let GGP
denote the minimum cardinality of a guarded guard set for P. So obviously this is the minimum number of guards needed to prevent theft from a gallery, from the patrons, as well as preventing theft from another guard. Okay. So initially there was
a theorem like this, and this is all happening right in computational geometry. We're very much divorced from graph theory, and graph theorists won't necessarily be aware of these results. And so there's this result that says if you have a simple closed polygon with n sides, then the number of guarded guards you need is at most the floor of 2n divided by 5. But that's wrong. Try that one. So we can just restrict it even if we don't put the guards on a vertex. Obviously, you need to put a guard right there. Do you agree? To guard this piece here. You have to somehow just put something right there. All agree with that? So that's happening there as well. It's also happening there as well. Okay. So there must be at least 3 guards in those extreme points. Looks like a horse or a dog or whatever in the dog's nose. There must be a guard there. Okay, so then you have to put, it's claiming it's 4, right? So now you just have to put an extra guard somewhere so that all the other guards are simultaneously guarded. And you see that's impossible to do that. There's no way to do that. So you delete at least another one, a 5th one. And so obviously this is wrong. So I didn't know about all these things. So I went to visit South Africa and was asking people. I don't know any results about total domination in maximal outerplanar graphs. Okay, so we just then looked at the graph theoretic version of this. So again, you can go and look at what's a dominating set. So a dominating set in a graph is just a set of vertices that if you take any vertex in the graph, then either V is adjacent to something, V is actually adjacent to some vertex in that set. Okay. And then the domination number, denoted by gamma of G, is the smallest cardinality of a dominating set. And then we all used
to the definition of a maximal outerplanar graph. And then the concept of domination was first introduced by
Burge and Orr, right? So that's dominating set. So of course, you don't have to have that. A vertex inside the set is dominated by something inside the set, right? So there's no guarding of vertices here. So that comes to the next idea of a total dominating set. So again, it's a dominating set. But what has to happen now is that every vertex inside the set has to be dominated by something inside the set as well. So that's exactly that definition here. And then the total domination number of a graph denoted by gamma T of G is then the smallest cardinality of a total dominating set. And then the concept of total domination was introduced by Cocaine, Dawes, and Dr. Edith Nimi, which is right here. Thank you, Steve, for giving us total domination. Although you said at some stage domination sounds bad, perhaps I should have called it total dominion. That sounds a bit better. But in any case, here's a happy little tree, so let's try to dominate this poor happy little tree. So, for example, you see that those 3 vertices would actually dominate the tree. So every colored vertex would be dominated by itself, and then all the other vertices would all be adjacent to something which is in the set. And you can't do it with fewer. So gamma T of that tree is going to be exactly 3. Gamma of T is going to be 3. Yes. And then the tree T with the shaded vertices form a total dominating set. So if you look at that, then that's going to be a total dominating set. And again, you can't do that with fewer, so gamma T of that tree is going to be 4. Okay. So we're back to Schwartal's results. Okay, so by doing that, of course, one of the byproducts of Fiske's proof, that very elegant proof of Fiske, is that the maximal outerplanar graph, well, you'd need at most n over 3 to actually dominate any maximal outerplanar graph. And so I showed you that, guarding, the guarding of the guards problems in a simple closed polygon, that upper bound was incorrect. So they actually corrected that in the paper in 2003, appearing in the Journal of Computational Theory, Computational Geometry. And I can just quickly say, how they proved that. So they obviously tried to get break it into triangles again. They triangulated the graph or the polygon, and then they did a short induction proof. And how does that work? For example, they looked at all the small cases. So the result is now it's at most 3n minus 1 over 7. That's the floor of that. And so, for example, they looked at a few small cases to set up the induction. So, for example, m equal to 6. They can show that either that or that set is a total dominating set of G for some vertex W. And if you compute, you replace the n with 6, and the number of vertices with 6, you get 2 vertices. For m equal to 7, again, you get that 3n minus 1 over 7. The ceiling of the floor of that is going to be 2. The same with 8, and the same with 9. So that takes care of all the numbers between 5 and 9. 5 is very simple to show because that's just the fan. And for a fan, you can also show that the total domination number is exactly 2. And then O'Rourke in 1983, that's to set up the induction part. If you start with any maximal outerplanar graph, you can always show that there's a diagonal edge, and the diagonal edge appears right here. Right? There's always such a diagonal edge, such that you can break up that maximal outerplanar graph into 2 outerplanar graphs, Tm and then Tn minus m plus 2, where the maximal outerplanar graph Tm will have the number of vertices would be between 6 and 9. Now remember, we already covered those between 6 and 9, so you can already say what is the total domination number for the smaller piece. And then, of course, you set up your induction assumption. You can play around with induction assumption on the other piece. Now, depending on, so you now start and assume you have a maximal outerplanar graph, at least 10 vertices, and you break it up in this way, and then depending on the smaller piece, you're going to have 4 cases, either 6, 7, 8, or 9. You're going to either use Tn minus n plus 2, or Tn, or when you actually contract the edge xy. And you can see that the final total domination number is going to be smaller than the total domination number of those 2 pieces. And then show that that is eventually, at most, the floor of 3n minus 1 over 7. So that's how they proved it. Okay. But that was all done not using graph theory notation at all. Okay, so it's just somewhere there in the literature, was always there. Okay, so remember that's the art gallery that gives us all the problems, which is the counterexample to the so-called proof that this is at most 2n over 5. Just look at those. If you triangulate that art gallery, right, you actually get the 2 maximal outerplanar graphs H1 and H2. You can quickly see that always happens. And now, independently, not knowing of anything about this, we prove the following result. So if G is a maximal outerplanar graph of order at least 5, and G is not one of those exceptional outerplanar graphs, which you can actually get from triangulating that problematic art gallery of order 12, we can show that gamma T of G is at most 2n over 5. And we can also show that this upper bound is best possible. Okay. So I'll just quickly sketch the proof. Fan of order n. It's just it's what it is. You just take a vertex and you have a path, and you join that vertex to every single vertex on the path, and you have your fan, right? Okay. So how does it work? We also use induction. Well, we don't use induction, actually minimal counterexample. So if you have a fan of 5 vertices, then obviously you can dominate the fan with only 2 vertices, totally dominate with 2 vertices, and that's equal to 2n divided by 5. And now you suppose the result's not true. So if it's not true, you have a minimum integer n, at least 6, and a maximal outerplanar graph, which is not one of the exceptional graphs, for which the total domination number is more than the floor of 2n divided by 5. And then among all those possible candidates, what we do is we choose a graph with the fewest number of vertices of degree 2. So that's how we set up the proof. Okay, so eventually, hopefully, we'll get a contradiction. So this assumption was wrong, and we have our result. So we had various claims, and I'm not going to go through all the claims. The first is that if you have anything but n congruent to 2 mod 5, you immediately get a contradiction. So what has to happen is that all the orders must be congruent to 2 mod 5. And you see it's gearing towards that maximal outerplanar graph of order 12 corresponding to the exceptional art gallery. And then again, you can't also have those two maximal outerplanar graphs occurring. I'll just leave it there. That's helpful in establishing the proof. And then we can actually associate every maximal outerplanar graph with a tree of maximum degree 3, and the vertices of which correspond to the triangles of H, and then 2 vertices being adjacent when the corresponding triangles have a common edge. So it's like a weak dual, I think that's what they call it. In the rest of the, we let T be a tree associated with this graph G, and note that the leaves of T corresponds to the vertices of degree 2 of G. Okay, so you have an X, you can just go back here, for example here, you'll have a vertex right there, and then you have, you can actually put a vertex there, and a vertex there, and you'll just have a path of order 3. That's the tree corresponding to that maximal outerplanar graph. And you see that this n triangle corresponds to that vertex of degree 2. And then the next thing that we can show, which is very useful in reducing the number of trees or the size of the trees, is that we can show that every leaf of this tree is a distance at most 4 from a 3 vertex, right? And so we have lots of trees that we have here. Those are trees T0 through to trees, and I'm getting blind, so let me see, what's that last one? Oh, it's T14. Okay, so we have those trees, and then we can show that these trees cannot occur as subtrees in the tree corresponding to our minimal counterexample, which will then give our results. So let me just show how we eliminate each of these trees and make sure that they cannot occur. For example, here we have the claim 4 then, which says that T does not contain any of the trees depicted above as a subtree. So here we have our first case, it's T0. And with that first subcase, T0, we have the maximal outerplanar graph which occurs. Now you see it does, so of course you put your vertex right there, the vertex there, and the vertex there, and you have this P3. And we can't have anything over here because otherwise it extends the tree, right? So there's nothing down here, there's nothing down here, because again, if there's another triangle over here, you'll have a P4 occurring. So if there are any other vertices occurring, it must be around there. Okay. Now we are assuming that that we have at least 7 vertices, so something at the top must occur. So without loss of generality, just assume that something is going out of here. Oopsie, what do I do now? Okay, but in any case, there's a blue part now, just ignore it. Technology is taking revenge again. Okay, so in any case, so there, the rest of the graph is right here, and so we just look at a few cases that could occur. What we do is we just assume that this one now has at least another edge coming out of here, and then we break this edge here, and we pull this vertex down here, and then what I do is I form this triangle down here. Now what could happen is, in this process, I suddenly arrive at my forbidden outerplanar graphs, H1 and H2. And if that happens, you can just quickly check that if this happens, then you can easily verify that gamma T of G is equal to 4. Which is equal to 2 times 12 divided by 5. I'm not sure. Yeah, that's probably because of. Okay. Yeah, I've had a brain attack here. I'm thinking about something else now. But in any case, it must be correct because everybody agreed with the referees at least agreed with me. So let me not have second thoughts about what I wrote here. And then the next thing is, now of course by doing this, I removed this vertex here. This was a degree 2 vertex. I'm not messing with that vertex here. And I'm breaking this here. And what happens eventually if you do this process, what's going to happen, this graph has fewer degree 2 vertices, and it's not one of the exceptional graphs. And remember what happens then we can assume that, well, gamma T of that is exactly at most 2n divided by 5, at most that. And then next what we assume is that this U2 is in the minimum total dominating set, which then tells me that gamma T of G is at most the floor of 2n divided by 5, which is what we wanted. Okay, so obviously this cannot occur, and then you have similar proofs for each of those other trees. And then lastly, after trying to eliminate all those trees as possible subtrees for the tree, we just look at the following. We take 2 leaves. Any maximal outerplanar graph has always at least 2 vertices of degree 2. So obviously the tree will have then 2 endpoints, and you take those at maximum distance from each other. There must be a 3 vertex somewhere on that path, and you choose then the endpoint which is to the nearest 3 vertex. And then choosing it appropriately, you see that in that tree what occurs is one of those previous trees that we try to eliminate. That gives me the contradiction. And then, of course, we have our result. So that's totally different from what O'Rourke did with that induction argument. We can also show that this is best possible. For example, there we have a first example right here. and we just need 2, and then you can use these graphs to create bigger graphs to show that you can actually get the upper bound in all cases. For example, here we can look at what we did here. Suppose n is congruent to 0 mod 5, and let H5 be that maximal outerplanar graph of order 5, it's right there. And then to create a order 21, you can just add another copy there, and you start gluing them together. There's a copy of H5 again, copy of H5 again. You can just also just triangulate there. And by doing that, you can always show that you can get the upper bound for every possible multiple of 5. And then if it's not 5, you just use these other graphs as building blocks. And so you can actually get for every single order, show that that's best possible. Now, I showed you the techniques used by Michael and Pinshu, and then recently I had a paper to referee from Lemanska, Zazu, and Zielinski. Lemanska and Zielinski are they're in Gdansk in Poland, and Zuza is at UNAM in Mexico. And they also provided an alternative proof for this result of myself and Dorfling and Jonk. But what they then did is they looked at a very similar technique used by O'Rourke. Again, looking at that diagonal that they find, and then they break up the maximal outerplanar graphs into 2 pieces, and they have a more intricate, induction argument. But that's much more difficult than the original result. So it was pleasing to see an alternative proof for our result. And then recently, Alvarado, Dantes, and Rotenbach. Rotenbach is in Germany, and the first 2 authors are in Brazil. They also provided a common generalization of the 2 results which I was talking about in this talk. And how did they do that? So let me just define this type of domination. Now, I know some people hate the domination folks for defining all sorts of variations, but this is actually useful because obviously it's going to try to combine 2 results, right? And so for some positive integer k and graph G, a set D of vertices is a k component dominating set. If every vertex in outside the set has a neighbor inside the set, it's obviously dominating, and then every component of the subgraph of G induced by the dominating set has order at least k, right? So if k is 1, right, nothing inside the set has to be adjacent to anything in the set. So that's just normal domination. If k is equal to 2, then obviously every vertex must live in a component of order at least 2 in the subgraph induced by D. So obviously that is total domination, right? So the minimum cardinality of a k component dominating set of G is, and they call that the k component domination number, gamma k of G. And they do apologize in their paper for using gamma k of G, but they said that at least in that paper it's clear from context, because obviously gamma k of G has been used for many variations of domination. So, so that's what I already said. For k equal to 1, gamma 1 coincides with the domination number, and gamma 2 of G coincides with the total domination number of G. So I'm not going to bore you with the details of how the following class or family of graphs are constructed, but they do, for every k, they specify a set of graph, script h of k, of order at least 4k plus 4, and at most 4k squared minus 2k. And then they use that description, or that set of graphs, to describe the following theorem. Okay. Now notice, if k is equal to 1, things don't work out, right? Because then we have that 4k plus 4 is bigger than 4k squared minus 2k, in which case the set of graphs, hk, would be empty. Okay, so there's no restriction if it is indeed when kappa is 1. And if you do that, then what you see is that gamma k of g, and the next, sorry, I've made a mistake there, the second line should be the floor, okay? So gamma 1 of g is less or equal to the floor of n divided by 2 times 1 plus 1, which is NO3, which is the floor. That's exactly Schwartal's result. And there's no restriction, right? And for k equal to 2, then, well, then you actually see that this H2 gives you those two restricted graphs that we talked about earlier, which is the triangulation that corresponds to our offending art gallery. And so in that case, the result then becomes gamma 2 of g is at most, and they then say it's a ceiling of, I must have just messed this up. I have to just go look at that again. But in any case, just indulge me. So it's 2 times n over 5, right? So that also then implies the result of Dorfman, Hattingh, and Jung. So I have to go and fix that slide. But in any case, that's the idea that I want to talk about. So it's interesting that, you know, this result was already in the literature wrong. They corrected it. Obviously, it was not the correct upper bound. We corrected it without knowing about what they did. And then, you know, we made the connection. And then we have this follow-up paper with a different proof, and then also trying to generalize the two different results, both for domination and total domination. So that's what I wanted to say today. Thank you.
So in computational geometry, there's a whole industry of art gallery type problems. Do any of the other formulations? Are there any translations of the other formulations, or any ones that you wish to translate?
I didn't see any others. I know they do various types of things. So obviously, you know, you can do much better than the graph situation, because you can place, as I said, you know, for example, you can place a person in the middle of the room, right? You're not restricted at the, so obviously it's going to be, but they also look at three-dimensional art galleries and all that sort of stuff. I'm sure there must be other, you know, connections as well. But yeah, so.
Questions? Well, could you permit me just a very brief story? Once upon a time. Make it about 1970. How did total domination come about? It's really an interesting story.
Yes, interesting.
I had just arrived in Oregon to be department head of computer science.
Yes.
The math people knew I did graph theory. Would you like to come give us a talk? I said, okay, I'll talk about domination. What else? And I mentioned chessboard applications. And in giving that talk, there was sitting in the back of the room this professor of psychology named Robin Dawes. I didn't even know him. And at one point I mentioned, how many queens does it take to cover an 8x8 chessboard? And everybody knows it takes 5 queens. So in those days, there was no email. So you got this little envelope and you sent campus mail. And everybody, they delivered, right? I got this little note from this guy named Dawes. He says, is this interesting? It was an 8x8 chessboard in which all 5 queens were on the main diagonal. And you can do that yourself if you try it, right? I'm not going to tell you where to put them, but you can put 5 queens. It is best possible, right? And he said, is this interesting? And that was all he said. And I said, yeah. So I sent it to Ernie King Victoria, and I said to him, is this interesting? And he wrote back, yeah. So we immediately knew we're talking about total domination. Now there's 1,000 papers on this one idea. And the funny thing is, I never met the guy. like. But I sent him a campus mail says, would you mind if you put your name on this paper because of your question? He said, yeah, that won't ruin my career.
Well, thank you very much.
Any other questions? If not, let's thank you. Okay.